Okay, in the last class, we began to discuss the wave functions of the orbitals, and we covered thus far the s orbitals, the 1s, the 2s, and the 3s, as well as the 2p and the 3p orbitals. Now, in the very end of the last class, we began to discuss the d orbitals, and we covered only one, that was the 3dz square orbital. We saw that the 3dz square orbital is a function of theta, so therefore there must be angular nodes. And we then saw that in this case, we have actually two conical nodes, because when we transform that angular part of the wave function from polar coordinates to spherical coordinates, then this part of the wave function is a function of 2d squared minus x squared minus y squared, and that describes, well, the cone. Okay, so that explains the characteristic shape of the 3dz square orbital. We have two lobes that have the same algebraic sign, and these two lobes are being separated by a toroid ring, which has the opposite algebraic sign. And there are two conical nodes, these two cones here, in between the two areas that have opposite algebraic sign. Okay, now let's go to this 3d x squared minus y squared orbital. So the wave function has this form here. Let us analyze it. We see again that the angular part of the wave function is a function of the two angles, and the radial part of the wave function is a function of this exponential term, this r squared term, and this simple coefficient here. So let us look at the angular part of the wave function, and let us transform it into Cartesian coordinates. Then it has this form here. It is a quarter times the square root of 15 over pi times x squared minus y squared over r squared. So now we have nodes when this function becomes 0. So this function becomes 0 when x squared minus y squared is equal to 0. And that is now the case for x being equal to 0, or x is equal to, x is equal to y, or x is equal to minus y. So we have two possibilities here, so we would expect two nodes. Okay, and these two nodes are planar nodes between x and y, so they bisect the xy plane, and z is variable, so the two planes extend into the z dimension, and that gives the x squared minus y squared its characteristic shape. Okay, so the electron density is mostly located in the xy plane. Precisely, the electron density is located on the y-axis and the x-axis respectively. There are two lobes of the same algebraic sign on the y-axis and two lobes that have the same algebraic sign on the x-axis. So in between, there are the two planar nodes. Okay, so the first planar node bisects the x and the y-axis. Okay, and the other node also bisects the x and the y-axis, but in a different position. Okay, so therefore the first planar node is here. Okay, and the other planar node is actually here. Okay, so one node stands for the condition x is equal to y, and the other nodal plane stands for the condition x is equal to minus y. We can also have a look at the radial part of the wave function more closely, but there's actually nothing new to learn. It's actually the same as in the previous case, okay, for the 3D c square orbital. So the radial part of the wave function is exactly the same. So there's nothing new to learn about it. Okay, now what about the three remaining d orbitals? The 3dyz, the 3dxz, and the 3dxy. So the radial part of the wave function is again the same as for the other 3D orbitals, so we're not discussing it in greater detail. However, it is worthwhile looking at the angular parts of the wave function. So we see them here directly in Cartesian coordinates. Okay, so the transformation from polar coordinates into Cartesian coordinates is already done. And you see that for the 3dyz orbital, this function is a product of y times z. Okay, so now when does this function become 0? Well, either when y is equal to 0, because then that entire product becomes 0, or when z is equal to 0, then also the entire product becomes 0. So now when y is equal to 0, then y is equal to 0 only in the xz plane. Okay, therefore the xz plane describes one planar node, and z is equal to 0 only in the xy plane, and therefore the xy plane is our second planar node. Okay, so now similarly for the 3dxz, the angular part of the wave function is, well, a function of x times z. That also gives the orbital its name. So on the side you also understand why the orbital is actually called this way. So that implies also two planar nodes. So this wave function becomes 0 when x is equal to 0 or when z is equal to 0. So x is 0 in which plane? Can anybody tell me?
YZ plane?
Wait a moment, please. Wait a moment. I made a mistake. I cannot hear you. Okay, now I can hear you. Can anybody tell me?
YZ plane?
In the YZ plane, correct. And z is 0 in which plane?
XY.
XY plane, correct. Okay, so these are our planar nodes in this case. And for the 3dxy, well, our angular part of the wave function is a product of x times y. So this wave function becomes 0 for x is equal to 0 or y is equal to 0. So x is equal to 0 in the yz plane, which is our first planar node, and y becomes equal to 0 in the xz plane. Okay, so now these nodes again give these three orbitals their characteristic shape. Okay, so the 3dxy looks similar than the 3dx squared minus y squared because it has two lobes of the same algebraic sign. But these two lobes are now located in between the axes, okay, and two other lobes of the same algebraic sign that are also now in between the x and the y axes. Okay, that is because the nodes are now on the x and the y axis. So that means that the 3dxy is actually rotated by 45 degrees relative to the dx squared minus y squared within the xy plane. Okay, so similarly, the 3dxy has four lobes, and these four lobes are in between the x and the z axis. Okay, because the the YZ and the XY axes, they are the nodes. And for the 3D YZ, we have also 4 lobes, but it's just that the orbital is oriented again differently. So now the lobes are actually located in between the y-axis and the z-axis. Okay, now of course there would be more orbitals to consider, for instance the f orbitals, but we do not want to go that much into the detail here. I think you understand the concept, how you can rationalize the wave functions of the orbitals and how you can actually understand the shape and the size of the orbitals. And this was the main point here. Now, just at the very end, let us consider, can we predict the number of nodes in these orbitals from their quantum numbers? And the answer is that is possible. And it's a fairly simple process. So generally, the number of radial nodes is given by the formula n minus L minus 1. So n is the quantum number n, and L is the quantum number L. And the number of angular nodes is just equal to the number of the quantum number L. Okay, so therefore, for a p orbital, which has the quantum number L equal to 1, we know that the number of angular nodes is equal to the quantum number 1. So actually there is here a mistake. So that shouldn't be spherical nodes. Okay, so that needs to be the angular nodes. Okay, I need to correct this mistake here on the slide. And then the total number of nodes is always n minus 1. Okay, so that means when n is equal to 4, for instance, we know that this orbital must have 3 nodes, and these nodes will either be spherical or angular, depending on what the quantum number L is. Okay, then we would be finished with this subchapter about the orbitals in the hydrogen atom, and we can now move over to the next chapter, which will be about multi-electron atoms. But before we go that, we still want to discuss one thing, in which is the orbital energies of all the orbitals that we have discussed in the hydrogen atom. Okay, so the Schrödinger equation is also capable of predicting the orbital energies, and the outcome is that the orbital energies are only a function of the quantum number n. So they are not a function of the quantum number L and the quantum number m. So that means that all orbitals that are on the same shell, okay, K, L, M, N, associated with the quantum numbers N, 2, 3, 4, and so on, have the same energy. So in this regard, the results of the um, um, Schrödinger model of the H atom is the same as the result for the Bohr atom model. Okay, and in a way that has to be so, because otherwise the atomic spectra could not be explained by the Bohr atom model. The atomic spectra are an experimental observation, and that experimental observation must be corroborated by the theory, of course. Okay? Regarding the atom model, regarding whether we choose a Bohr atom model or a quantum mechanical atom model. So again, the energy is a constant over n square, and the 1s orbital has the lowest energy, which is minus 13.6 electron volts. So the energy of orbitals usually provided in electron volts, because that is a convenient energy unit for orbital energies. So if you want to know what this is in joule, then this is 1.602 times 10 to the minus 19 joules. So this is a very small energy units, which is useful for very small energies, and orbital energies are generally very small. Okay, so the 1s orbital is the lowest energy of minus 13.6 electron volts. So then the 2s and the 2p orbitals have the same energy. They have a quarter of E1, so that at first glance looks like a smaller energy, but it's actually a higher energy because of the negative algebraic sign here. And the negative algebraic sign is again because these orbital energies are binding energies. So adding an electron to a proton to give the hydrogen atom is an exothermic process. So this is another way to understand the negative algebraic sign. So then all the orbitals in the third shell would have 1/9 of the energy of E1, and all the orbitals in the fourth shell, in the n shell, would have 1/16 of the energy E1, 1/16 of minus 13.6 electron volts. So that means, and I'll just say this again, that in the hydrogen atom, all orbitals with the same quantum number n are degenerate, and the quantum number L and M has no effect on the orbital energies. But now let's go from the orbital energies of the hydrogen atom to the orbital energy of multi-electron atoms, and we'll see that the situation will be different then. We will understand shortly why. So the Schrödinger model is also able to give the orbital energies for multiple electrons, for atoms with multiple electrons, and precisely it is given by minus z squared times 13.6 electron volts over n squared. So n squared, or so n is nothing else but the quantum number n, and z is nothing else but the number of protons. Essentially, that energy is defined by the Coulomb interaction between the electron and the protons in the nucleus. And the more protons we have, the greater the orbital energy is. Okay, we should keep in mind here, though, that the Schrödinger equation can only be solved for one-electron systems, not for multi-electron systems, and we cannot account for electron-electron interactions, as we will see in a moment, this has profound consequences for the orbital energies as we observe them in experiment. Okay, so now this factor 13.6 electron volts is just because when we insert n is equal to 1, okay, then this term here, all these constants multiplied with the other gives minus 13.6 electron volts. Okay, and then En for a multi-electron atom is just d square times 13.6 electron volts. All right, so now let's go to the most simple multi-electron atom, the helium atom, which has 2 protons at the nucleus and 2 electrons around it. So according to this equation here, the energy of the electrons in the helium atom should be, well, 2 square, because the helium has 2 protons, times 13.6 electron volts over 1 square. So that should be, and of course minus, and that should be minus 54.4 electron volts. Okay, so now we can experimentally check if this is true by measuring the first ionization energy of the helium atom, because the first ionization energy is minus the orbital energy. That is because the ionization energy is the energy that is required to remove the electron from the orbital, and the orbital energy is nothing else but the energy which is released when you add back that 1 electron to the orbital. Okay, what is the experimental result? The experimental result is that the ionization energy is 24.6 electron volts. So this is much less than we would expect. We would have expected that it is plus 54.4 electron volts. So however, when we take a helium plus ion and remove the other electron, then that ionization energy is exactly 54.4 electron volts. So both electrons are, of course, in the 1s orbitals. So why is the ionization energy for the first electron higher than the ionization energy for the other electron? And the answer is that now what the Schrödinger model does not take into account is electron-electron interactions, because it can only be solved for a 1-electron system. For any multi-electron system, it becomes mathematically too complicated. So of course, now these electron-electron interactions are repulsive. The electrons repel each other, and for that reason, the binding energy for these electrons is less. Okay, and that means also that the orbital energy is less when we're considering 2 electrons and the electron-electron interactions. So in other words, we can say, phrasing this a little bit differently, we can say that the first electron shields some of the nuclear charge from the second electron, so that the second electron doesn't experience the full attractive positive nuclear charge from the nucleus anymore, but only a reduced nuclear charge. We also call it the effective nuclear charge. So now for the helium atom, this effective nuclear charge for the second electron is 1.34. You see that's smaller than 2, the formal positive charge of the nucleus. So we can easily calculate that? Because the energy of the electron must be Z square effective over N square times 13.6 electron volts, which must be minus 24.6 electron volts, because the ionization energy for the helium atom is 24.6 electron volts. Okay, so now we just need to solve this equation here for Z effective, and then Z effective the square root of N square over 24.6 electron volts over 13.6 electron volts. And that's 1 square over 24.6 electron volts over 13.6 electron volts. And that is 1.34. Okay, now let us move over from the helium atom to the lithium atom. So when we look at the lithium atom, we have to take the Pauli principle into account, which says that an atom must not have electrons with all quantum numbers being identical. Okay, so the lithium has 3 electrons, but now these 3 electrons cannot be filled into the 1s orbital anymore. Only 2 of them can be filled in the 1s orbital. The third one must go into another orbital. Okay, and that would be the orbital of the next higher energy. So which orbital would that be? Okay, now I've learned previously that the orbital energy, according to the quantum mechanical atom model, should only depend on the quantum number n, not on the quantum number L or M. And that means that the third electron could now go either into the 2p orbital, okay, or in the 2s orbital. So what do we experimentally find? We find experimentally that our electron is in the 2s orbital and not in the 2p orbital. So that means that the 2s orbital in reality is actually energetically lower than the 2p orbital. This is something the Schrödinger model could not predict. But we can again explain this using the concept of shielding effects and the effective nuclear charge. Okay, so in fact, the 2s orbital penetrates the inner 1s orbital slightly better than the 2p orbital does. Okay, and for that reason, the 2s orbital experiences a somewhat greater effective nuclear charge than the 2p orbital. And for that reason, the energy of the 2s orbital is somewhat lower than the energy of the 2p orbital. So this is visible from this graph, not at first glance, but at second glance. So you see actually that the big electron density maximum of the 2s orbital is a little bit further away from the nucleus in comparison to the electron density maximum for the 2p orbital. So that would argue that, well, the 2s orbital would not penetrate the 1s orbital better than the 2p orbital. However, the 2s orbital, he has this second maximum very close to the nucleus, which penetrates the 1s orbital very, very effectively. And that's the reason why the 2s orbital penetrates overall slightly better than the 2p orbital. And therefore, the 2s orbital has a slightly lower energy than the 2p orbital, but not much. Okay? So therefore, the electron configuration of the lithium is 1s2 and 2s2 and not 1s2, 1s2, 2s1 and not 1s2, 2p1. This is the explanation why the third electron of the lithium is in the 2p or as 2s orbital and not in the 2p orbital. Okay, so now these considerations can be extended to other multi-electron atoms. We can generally say that when we have electrons of the same quantum number n, then the energy of the s orbitals are lower than the energy of the p orbitals, which are lower than the energy of the d orbitals, which are lower than the energy of the f orbitals. And that is because the effective nuclear charge increases from f to s, and the penetrating ability increases from f. The penetrating ability decreases from F to S. Okay, so when you have a 3D subshell in a multi-electron atom, for example, the degeneracy of the orbitals with the quantum number n is no longer valid. The 3s orbital has the lowest energy, the 3p orbitals have somewhat higher energy, and the 3d orbitals have the highest energy. Okay, so now it would be, of course, great if we could find a simple method how to estimate shielding constants, because that would allow us to calculate effective nuclear charges for electrons, and that would allow us to calculate energies of electrons and orbitals, and that would be very helpful to explain electron configurations. And a very simple method that can do this is the so-called Slater rules that estimate shielding constants sigma that can be used to estimate effective nuclear charge. Note here that the rules that we discuss are qualitative estimates based on relatively simple assumptions. They are not really accurate calculations, but for many purposes, these estimations are very useful. Okay, so the idea is that we can calculate an effective nuclear charge from the shielding constant, and the effective nuclear charge would be nothing else but the real nuclear charge of the atom minus the shielding constant. So now, how to calculate sigma? According to Slater, we can do this in 3 steps. So the first step is that we write out the electron configuration of the atom in the following order and groupings. So we write out the electron configuration according to quantum numbers. Okay. Note that this is not exactly the same as writing out the electron configuration according to energy. In many cases, it's the same, but not in all cases. So we start with 1s, followed by 2s and 2p, then there's 3s and 3p, and then there's 3d, and then there's 4s, 4p, 4d, 4f, 5s, 5p, and so forth. Okay. Now we put orbitals that have approximately the same energy, okay, similar energies, in parentheses. So 2s and 2p orbitals of the same s and p orbitals of the same shell have very similar energies. So we place them in parentheses. See that here. All other orbitals remain their own group. So d orbitals always remain their own group. F orbitals remain their own group. Also 1s orbitals form their own group. So now, secondly, we distinguish between 2 cases. the first case is when we look at an S or a P electron, and the second case is when we look at a D on F electron. So let us first consider electrons that are either in an S or in a P orbital. Okay, and we want to calculate the shielding constant for that particular orbital, for that particular electron. So then we say that any electrons to the right of that group contributes nothing to the shielding constant. So this is a good estimate because electrons to the right of the group are further away from the electron that we look at. So these electrons will probably not shield at all, and therefore they will not contribute anything meaningfully to the shielding constant, any good approximation. Okay, so then any other electron which is in the same NS and P group contributes 0.35 to sigma. Okay, so these electrons have approximately the same distance to the nucleus as the electrons that we look at. Therefore, we assume partial shielding of a full nuclear charge. A good approximation is to assume about 35% shielding of a full nuclear charge, full elementary charge, and that is equal to 0.35. So now the third rule is that each electron in the n minus in an n-1 shell contributes 0.85 to sigma. So these electrons are now significantly closer to the nucleus compared to the electron we look at, and for that reason they shield approximately 85% of a full elementary charge. Okay, and any electron in an n-2 shell or below contributes 1.0 to sigma. So these electrons are so much closer to the nucleus than the electron that we look at, that they fully shield an elementary charge, positive elementary charge from the electron. Okay, so now for N and D electrons, we have slightly different rules. The first rule is again the same, which says that an electron to the right of the N or D electron we look at does not contribute anything to sigma, and that's again because these electrons are further away from the nucleus in comparison to the electron that we look at. But now secondly, each of the electrons in the same group contribute 0.35 to sigma, so that will also goes analogously to the previous one. In the same group, the electrons have approximately the same distance from the nucleus, so they partly shield an elementary charge, approximately 35%, or 0.35. And thirdly, and that's now a difference, each electron to the left of the D electron or the F electron we look at contributes 1 to sigma. So it shields a full elementary charge because it's significantly closer to the nucleus. All right, so now let's apply these rules and let us check what we can do with them. So here's a simple example, oxygen. The question is, what is the effective nuclear charge for a 2p electron of oxygen? So in the first step, we need to write out the electron configuration according to the Slater rules. So the electron configuration is 1s2, 2s2, 2p4. We have to place parentheses correctly. So the 1s orbital would be its own group, but the 2s and the 2p orbitals would be grouped together. So this would be the first step. Now, the second step is the calculation of the effective nuclear charge from the shielding constant. So what is the shielding constant? So we look at one of the p orbitals here, okay, and determine, well, how well do all the other electrons shield the nuclear charge from this p electron. So now Z is equal to 8, okay, because oxygen has 8 protons. And we must subtract now, well, 5 electrons which are in the same group. Okay, so here we overall have 6. 1 is the electron we look at, so that leaves 5. And these 5 contribute with a factor of 0.35. Okay. Now, secondly, we need to consider these 2s electrons, and they are in an n-1 shell, and therefore they contribute 0.85. Okay, now what does that give? Well, that gives overall 4.55, which is the estimated effective nuclear charge for that 2p electron. Okay, now we could, for instance, also ask what's the effective nuclear charge on a 1s electron of oxygen. So now when we look at one of these two, and that means that we can ignore these 6 because they are in a group to the right of the electron that I look at. Okay? We only need to look at the shielding effect of the other 1s electron. So that means that the effective nuclear charge would be 8 minus 0.35, which is equal to 7.65. Okay. So now we see that the effective nuclear charge on the 1s electron is much higher than the effective nuclear charge on the 2p electron, and that also makes sense because the 1s electron is much closer to the nucleus than a 2p electron. Okay, one can do more than this. One can predict ground state electron configurations. So for instance, we know that the ground state electron configuration of potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d1 that we know from the experiment. Okay, but it's not so obvious that this is the ground state electron configuration. We could also say, well, why isn't the ground state electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d0, 4s1? Oh no, actually I made a mistake, of course. That is the real electron configuration, right? The second one. So the potassium has 1 4s valence electron. It does not have a 3d valence electron, okay? But of course, one could think, well, why is that, right? Given that that d orbital has a lower quantum number n in comparison to this s orbital here. Okay, so obviously the energy of 4s must be lower than the energy 3d, but can that be calculated somehow? And the answer is yes. The Slater rules, even though very simple, can confirm that. So let's just do this for the two cases. Now for the first case here, the effective nuclear charge on that 3d electron is 1. That is because the real nuclear charge for the potassium is 19, and all the other electrons here are in an n-1 shell, and for that reason they fully shield. Okay, we have 18 of them, so we have 18 times 1, and 19 minus 18 times 1, well, that's 1. So now what about the other electron configuration. So now we look at a 4s electron, and we must apply the Slater rules for s electrons. Okay. So now we have no other electron in the same shell, in the same group. So we do not have an electron that contributes with a factor of 0.35. But we have these 8 electrons, which are in an n-1 shell, which contribute 0.85. Okay, so this actually has to be a multiplication sign here, not plus. I'm sorry about this mistake also. No, I'm sorry. Incorrect. So we have 8 times 0.85. Of course, that's correct. Okay, now we have to add that the other 10 electrons, okay, and these are now in an n-2 shell, and therefore the shielding factor is 1. So we have 8 times 0.85 plus 10 times 1, and that gives 16.8. So the effective nuclear charge is 19 minus 16.8, and that is 2.2. Okay, now knowing this, we can also calculate the orbital energies. According to the formula, E is Zf squared over n squared times 30.6 electron volts. So for the first electron configuration, our effective nuclear charge is 1. So we have minus 1 squared times 13.6 electron volts over the quantum number n, which is in this case 3, because we have a 3d electron. And that gives minus 1.51 electron volts. So now, for the 4s electron, our effective nuclear charge is 2.2. So we have minus 2.2 squared times 13.6 electron volts over 4 squared. And now we have 4 because we look at a 4s electron. And that gives minus 4.14 electron. So we see indeed that the Slater rules can correctly predict that the 4s electron in the potassium atom is actually a lower energy than a 3d electron, and therefore the electron configuration should be 4s1 and not 3d1 for the ground state electron configuration. Okay, I think we can stop at this point.